So with this presentation, I would like you to present some results on regarding crack detection, actually segmentation of cracks in steel bridges using convolutional neural networks. So what's the general motivation behind the work is that general and detailed visual inspection are the most typical type of inspection that are carried out in bridge structures, and these are carried out periodically every 3, 5, 10 years, depending on the country regulation. But these are often characterized by a low reliability, and that's quantified, what you can see here on the right-hand side of the slide, by a probability of detection curve that relates the crack size to the probability of that crack being detected by an inspector, which is insanely scattered, and therefore induces a low reliability of inspection method. What you can think of is that what you can be considered a reliable detection for a crack of almost 5.5 inches. So it's pretty large. Besides these, general and detailed inspections are also characterized by high cost, due to trained personnel, potential closure of the bridge during inspection, depending on the type of structure, on where the structure is located, but also hazards and risk for inspectors that most inspectors that most of the time have to climb up a structure, but are also actually exposed to hazardous environments. Okay. So the general aim of this work is to improve general and detailed visual inspection by aiding interpretation of data by AI. So in this context, this would allow, for example, use of remote inspection by drone or crawling robots, for example. So methodology-wise, we perform this with the neural network, which is based on UNet, which is a typical neural network used for crack segmentation. The neural network takes as an input an image of a part of a component of the bridge, and is processed through an encoder, which is the descending part, and the decoder part of the network. There are some connection between the encoder and the decoder. Basically, the encoder extracts features from the image, and then this is so the features are reassembled, sort of say, and at the output of the neural network, we have a segmentation map. Segmentation map that indicates for every pixel a sort of value between a sort of probability. So it's a value between 0 and 1, indicating indeed whether that is a potential crack pixel or not. So this is based on is a convolutional neural network based on Kompanets that is based on UNet itself. So at the end of this process, after we have a training data set composed of crack and non-crack images, we could this training data set is also enhanced by some data augmentation procedure, which is typical for image processing. In the end, the output of the neural network is used for the evaluation of the segmentation with the test subset, which is an independent one. In total, we have collected 1,055 high-resolution images of crack in steel bridges. And for each of these images, we needed to perform a binary pixel segmentation map, meaning that for each pixel of the image, we needed to indicate whether that pixel was a crack or not. It's a pretty tedious work, but to do this, we have developed in the past a semi-automatic segmentation tool in which the user just needs to select crack endpoints, and then through geometric image processing and the tracking algorithm, edge tracking, then the segmentation map is automatically built. It's not perfect, but it's pretty accurate. So the first problem we encounter is that for training and evaluation purposes, the image of high resolution, where with high resolution, I mean some image that can be taken with the modern reflex, like, I don't know, 15, 20, 30 megapixel image, is too large to be processed from a neural network. To give you an idea, to process an entire image like this, we would need a GPU I would say, graphic board with about 200 gigabyte of GRAM, whereas the state-of-the-art graphic boards have between 40 and 80, depending on. So the computer at our disposal had about 40 gigabyte of RAM, of GRAM. So we needed to split the image in patches. So from now on, generally, we talk about patches, not really images. So for each patch, is evaluated by the neural network. And there is now a peculiarity of this problem as compared to other crack detection. Crack detection is a kind of a common crack detection using convolutional neural network has been explored very extensively in the past, but not really for steel bridges. Mainly for asphalt and for concrete. And there is a strong difference because cracks in asphalt or in concrete are visually larger. So they have the crack mouth has a way larger width. And usually they are crack networks, for example, in asphalt. This is a data set from Koenig. So instead, in bridges, cracks are, in steel structures in general, in metal structures, cracks are small and their extension is not like in asphalt. So there is a problem of imbalance of the data set, which is basically, which is basically that the number of crack patches is significantly smaller than the number of patches that do not contain cracks, so background patches. And this causes the neural network to learn to indicate everything as a background. So if you take UNet and you apply it as it is to patches taken from images, UNet will learn to indicate background. So to do that, basically this happens because the training of a neural network is an optimization process, and this large data imbalance causes stuck in local minimum. You can correct this by using loss functions, but it's very difficult to correct for this ratio of background versus crack patches. So what is a loss function? It's basically a loss function is used for the training of the neural network, which is the process in which the parameters of this numerical model are identified. So by using training data are fed to the neural network. So each image, together with the annotation, is fed into the neural network. The neural network creates segmentation. Segmentation is compared with the annotation. And then this allows us to calculate the loss function, which indicates the agreement between segmentation and annotation. It's a scalar, and then we can use it in an optimization procedure. Generally, training a neural network cannot be done with the normal optimization procedure, so there are specific algorithms for that. And then parameters are updated, the iteration go on and on until you reach an optimum. To give you an idea, these slides represents a background image, so without any crack. And we would be happy with the segmentation like this. It's a good segmentation, although there are some false positive, but segmentation is not so bad. And instead, on the right-hand side, we have a bad segmentation. There are too many false positives. With the use of common loss functions, we would expect a prediction of let's say 0, because these are all background images. But already for a good segmentation, the value of the dice score, so this dice, sorry, not the dice score, the dice loss function, is already as more or less, actually, it's the same value of for a bad prediction. So it's very hard to optimize. It's very hard to find the domain in which optimization can take place. And this is also explored for different loss functions. There is a focal loss function, could be a loss function that helps us for this problem, but it has 2 parameters to be evaluated, and training a neural network is time consuming. So you have to try over and over with many parameters in such a way, in the end, you probably get results. So this is very tedious. And you basically have a problem either of very quick saturation or very low gradient, unless you catch the right parameters. So we propose a different loss function, which is based on the dice loss function. So the one that is presented here, which basically in which we have an evaluation pixel by pixel between segmentation and annotation. And for every annotation pixel, we have a value of the segmentation, so the result of the neural network, which is a value between 0 and 1. So in the end of this evaluation of procedure, of all the images, we can calculate the loss function. When we have background patches, this is basically very near to 0. So the dice score is always 1, the dice loss function. So we invert the loss function when we encounter during the training a background patch. Inverting means you can imagine it as we train the neural network to detect the background rather than detecting crack. And that helps us a lot. So we train to be a background detector rather than a crack detector when a background image is on the show. And this helps us a lot because it's not spectacular gradient, but there is a gradient as compared to the other. So this allows to make the optimization of the parameters of the neural network. Now, to quantify how the neural network performs, a common indicator in image processing is the dice score. A dice score basically is a ratio between 2 times the actual crack pixels predicted as cracks and the total number of crack pixels in the ground truth and in the annotation. So the results of the neural net and in the prediction. So results of the neural network and the annotation map, the one that we feed in with our dataset. Well, we compare the dice score with the typical neural network, basic UNet, and this is a state-of-art convolutional neural network for cracks in asphalt. And we could see that with this loss function with inversion, we were able to have better results. We were able to have better results compared to state-of-the-art. What does that mean? Because dice score is not really something we deal with every day, right? So in this slide, you can see an image with the crack. I don't know if it's really visible. The crack is here. These are the ends which are marked by inspectors. You can see here the annotation of this crack due to the resolution of the image here. We see this continuously, but it's actually continuous. Basic UNet will predict like something like this. So there are many crack distractors, like, I don't know, these edges or the edges of the weld sometimes the shades of the lights and dirts that neural network tends to predict as crack. But already when we increase to roughly 90%, that's already a decent neural network prediction. And more or less, we get rid of these other distractors with this architecture of the neural network.
Dr. Leonetti, please summarize in 1 minute.
Yes,
please.
I am done. But that's not all good because also bad annotation come out of the work. So in this case, crack distractors were not able to be recognized. So we propose a convolutional neural network architecture based on UNet with the Kompanets backbone that aims to overcome a little bit state-of-the-art for crack segmentation that in steel bridges poses different challenges than in other structures. With the loss function, we avoid some difficulties in training and outperform the state-of-the-art UNet. But false positive segmentation is still an issue. And as outlook for future work, we aim to, let's say, overcome this issue by having first a crack detector and then a crack segmentor, and quantify POD curves for different hardware requirements. This is an example of a quantification of POD curve that we did in the past with this neural network. And that's all.